All right, well, this is the Exam 3 review, and just as in the last Go to Exam 2 review, I've pretty much picked out about 10 questions. I think it's a little bit more for this one that I think are some of the most missed stuff and also some of the most important stuff that we've covered since the last test. As a reminder, the topics for this exam are going to be electricity, magnetism, sound and waves, and then also light. So I'm just going to go ahead and get started. Whoops, that's not what I wanted. All right, so the first question, electricity question, we want to know what is the total resistance in a circuit that is two 5-ohm resistors and two 10-ohm resistors that are arranged in series. So I have the words in series in bold on this slide here, and that's because they're obviously the most important words for this problem. But on your test, they're not going to be in bold. We're not going to direct you to the most important words in that sentence. So be sure on the exam to read the problem very carefully when it's asking about total resistance, because this is one of the few equations that we'll have, or the few problems that we'll have, that has two different equations depending on the situation. So to solve for the total resistance in a series circuit, it is simply the equation R total equals R1 plus R2 plus R3 plus R4. And of course, that's for however many resistors we have in that circuit. So for this one, again, be careful with your reading because it says that we have two 5-ohm resistors and two 10-ohm resistors. It might be a common mistake to just read through this and say, okay, I just see 5 ohms and I see 10 ohms, going to add them together and get 15. So be careful to read very carefully through this exam. So in series is a very basic equation. You're just going to be adding them together. So we end up with 5 ohms plus 5 ohms plus 10 ohms plus 10 ohms. And that should give us a total of 30 ohms. All right, so the second part of this question says, what if they were arranged in parallel? We have the exact same number of resistors, but this time they're just connected a little bit differently. So when you go to your equation sheet, you'll want to look for the equation that says total resistance in parallel. And when you find that, you'll see that it's a little bit different because it's not just adding together the resistors now, it's going to be adding together the inverses of the resistors to get the inverse of the total resistance, which you can ultimately flip or cross multiply to solve for the total resistance. So I'm going to plug in my values, and again, just be aware that there are 4, even though there are only 2 numbers in the question. And we end up with 1 over 5 plus 1 over 5 plus 1 over 10 plus 1 over 10. So in order to add fractions together, we want to make sure the first thing is that we have a common denominator. So in this one, we could use 10. That probably would have been easier. I'm not really sure why I used 20 in this problem, but either way, should come up with the same answer. So we have to find a common denominator, something that you can multiply these numbers by to get the same number. So we have 20 ohms in the bottom, and then we want to find the equivalent fractions. So 1 over 5 is equivalent to 4 over 20 because it can reduce to 1 over 5. So in order to get that, I have to say, okay, what does how many times does 5 go into 20? And of course, the answer is 4. So I have to multiply 5 times 4 to get to 20. So I have to do the same thing to the top of my fraction. If I do something to the bottom of the fraction, I have to do the exact same thing to the top to make sure that they're equivalent. So 1 times 4 is just 4, and that's the same for both of my first two because they're both 1 over 5. And then you have to multiply 10 times 2 to get to 20. So I want to multiply the top of the fraction by 2 as well to get to 20. And so I end up with 4 over 20, 4 over 20, plus 2 over 20, plus 2 over 20. And I can add all of those together. And I end up with 4 remember, adding fractions, once you have that common denominator, you're only adding together the numerators. So 4 plus 4 is 8, plus 2, 10, and then plus another 2 is 12. So now I've gotten to the point where this is where some people will stop, hopefully not after the lessons in class and not after watching this review. But it's very easy to get to this point and say, okay, I just have a number on this side. I must be done with my solving. So we've solved and we've gotten 12 over 20. You could reduce it. You could say, this reduces to 3 over 5, but that's still not our final answer, because over here, we have not solved for the total resistance. We solved for the inverse of the total resistance. So I think it's easiest, just because it's a process that we do in other equations as well, that once you get to this point, you just cross multiply. And that way we can eventually solve for the total resistance. So 1 times 20 is 20, 12 times R total, and then to get the R total by itself, the total resistance by itself, divide both sides by 12, and you end up with 1.67 ohms, or that should be 5 over 3. Either one is fine to leave it in decimal or in fraction, as long as you reduce your fraction. All right, any questions on that? Okay. All right, another electricity equation, electricity problem. Most of the calculations for this exam are going to be with the under the electricity concepts. So this one's talking about transformers. And there are 2 different transformer equations, so you want to be careful of which one you're looking at on the equation sheet when to solve this, because they're set up a little bit differently, but they both have voltage in them. So they're easy to get mixed up. All right, so this one says that the primary side of a transformer has a voltage of 10 volts running through 5 turns of wire. If the secondary side has 50 turns of wire, what is the secondary voltage? So at this point, I just wanted to, before we solve this, I just wanted to remind you of what a transformer looks like and what the purpose of a transformer is. So the way that a transformer is set up is that you have two different coils or sets of wire that are put into loops, and they are electrically isolated from each other, meaning that they're not physically connected to each other, so that current can run through one and into the other one. So we have a primary side over here and then a secondary side over here. We introduce a primary voltage into this coil, and inducing a voltage creates a current through this wire. And we know that that current produces a magnetic field. And so once the current is introduced and once the magnetic field begins, it is introduced to the second side of the transformer or the secondary coil, and then that induces a current inside of there and outputs a secondary voltage. The reason that we have a transformer is to be able to either step up or step down voltage to safely enter into whatever that voltage is being applied to. So in this case, if we had fewer wires on this side, or fewer loops or fewer coils or fewer number of turns on the primary side and more coils on the secondary side, that's going to induce a greater voltage output than the original primary voltage. The number of coils, the more coils that you have, the greater the intensity of that magnetic field, which produces a stronger current and a stronger voltage. So the equation for this is that the turns ratio, or the ratio of the voltage on the primary side divided by the number of turns on the primary side, is equal to the turns ratio on the secondary side. So in this case, we have a voltage on the primary side of 10 volts running through 5 turns of wire. So that's all going to be on the primary side. And again, be sure to keep everything on the primary side on one side of the equal sign. So we end up with 10 volts divided by 5 equals a secondary voltage, that's what we're solving for, and then divided by 50 turns. So we want to know what the secondary voltage will be. So in order to do that, the easiest way to do this is to cross multiply. 50 times 10 is 500, and then 5 times the secondary voltage. Divide both sides by 5, and we end up with a secondary voltage of 100 volts. So you can see what I was talking about with the how the number of turns is related to the number of coils, because here, if we had more turns, we had 50 turns on the secondary side, and we ended up with an output of 100 voltage, 100 volts. And on the primary side, we only had 5 turns, and then we had an input of 10 volts. So it stepped up the voltage by putting more turns on the secondary side. Any questions on that? Okay. So the other type, another transformer problem is going to be on the next slide, and I just doing this to show you just how similar they can look, so that it's to show you how easy it can be to mix up the two different transformer equations. So using the same numbers, this one says the primary side of a transformer has a voltage of 10 volts and a current of 5 amps. If the secondary side has a current of 50 amps, what is the secondary voltage? So in this case, we were given a primary voltage. We're still asked for the secondary voltage. But the difference is here that we're not given the number of turns, we're given the current. So again, just be careful in reading. And if we go to our equation sheet, we will see an equation that should be titled something along the lines of power in a transformer. And the property of a transformer that this comes from is that the power into the transformer is equal to the power out. So since power is equal to current times voltage, we can rewrite this as current times voltage on the primary side equals current times voltage on the secondary side. In this case, I've named the primary side 1 and the secondary side 2, but I think it's labeled P and S on your equation sheet. So again, just be careful to keep everything on the primary side on one side of the equal sign. So we have 10 volts and a current of 5 amps on the primary side and a current of 50 amps on the secondary side. And we want to know what the secondary voltage is. So 5 times 10 is just 50, and then divide both sides by 50, and we'll end up with a voltage on the secondary side of 1 volt. And you can see it's always a good idea to go back and plug that back in, that the balance of having different voltages, because the currents are different, ends up making this equal so that the power in equals the power out. All right, any questions on that? All right. Okay, so with our study of waves, both light waves and sound waves, we have to be able to identify each of these types of angles that we have labeled on screen here. So the first one, this one labeled 1, which is the angle between the incident ray and the normal. What is that going to be called? I kind of just said it. That is going to be, number 1 is going to be the angle of incidence. So the incident ray comes in. Remember that this is the angle from the normal, which is an imaginary line drawn perpendicular to the surface. So if a light wave or a sound wave comes down and is striking the surface of water, that is the angle in between the normal and that wave. Number 2, this is between the reflected ray and the normal again. So it's this angle right here. So that one's going to be called the angle of reflection. And remember that our law of reflection says that the angle of incidence is equal to the angle of reflection on a smooth flat surface. So these are going to be the same. If you're dealing with something like, if light shines on the surface of a mirror or something like that, then you'll see that you can see that pretty clearly, and you probably saw that from your lab yesterday as well. All right, number 3, this angle down here is just a trick angle. There's nothing we're concerned with in this class. Maybe if you took geometry or something like that, you had to worry about that angle, but this is nothing of concern to us. Number 4, this is when light passes from, or light or sound, any sort of wave passes from one medium to another. It is going to bend due to the change in speed through different mediums. And that angle that it bends, again, relative to the normal, perpendicular to the surface, is called the angle of refraction. All right, now there are quite a few definitions for this section of the class. So first things all come down to electricity and magnetism and the relationship between the two. So we already kind of addressed when we were doing the transformer calculation example. What does a transformer do? And the definition that you want to keep in your mind for transformer is that it steps up or steps down voltage. Yes, Sarah? Go ahead, Sarah.
Oh, okay. Now I had a question regarding the what you were previously explaining.
Oh, okay.
Regarding the angle of refraction. Basically because angle number 3 and angle number 4 are so close together. So when we did the experiment, we had different angles that got refracted depending on the liquid that we were working with, like sugar and water and all of that. So wouldn't angle 3 be also considered like an angle of refraction?
The angle of refraction is the angle of incidence, angle of reflection, and angle of refraction are always measured from the normal. Of course, angle number 3 is going to change depending on how much it bends. But the official angle of refraction is always measured from the normal. That's by definition. It's not measured from the surface. That would be what 3 is. That would be the angle from the surface to the ray, the refracted ray.
Okay.
But always measured from the normal, which is this dotted line here. So it's this angle. And 3 and 4 always add up to 90 degrees, but the angle of refraction is the one that we're concerned with for this class.
Okay, so it would be number 4 because it's measured by the normal.
Right. Everything we're concerned with is going to be measured from this dotted line.
Okay. All right, perfect. Thank you.
Sure. Good question. All right. So we did what does a transformer do? What does a generator do? The main definition that we want to remember here is that generator converts mechanical energy into electrical energy. I often think of just like a simple hand crank where you just rotate the handle, and that's the mechanical motion, the energy of moving. And then what that does is it actually just moves a magnet near a wire that can carry current, and that induces a current because you have a changing magnetic field moving that magnet closer. And that induces a current, which produces electricity. So that simple process of a hand crank is going to convert mechanical energy and then output electrical energy. A motor we're probably pretty familiar with in our cars, and a motor does the opposite thing, or just the backwards thing is what a generator does, and it converts electrical energy into mechanical energy. So when you start your car, you know that it takes some sort of electrical energy and then it converts that into mechanical energy, the energy of motion for your car, all the moving parts of your car to let it run. All right. So those are three main definitions for the electricity and magnetism part. We also had a good number of definitions for sound. So resonance is our first one here. When does resonance occur? And the definition that you want to remember for resonance is that it's when an outside force matches the natural frequency of an object. This will be like the examples given in class with the Tacoma Narrows Bridge, where that outside force was a 40-mile-per-hour wind. It matched the natural frequency of the bridge, which ultimately increased the amplitude of the bridge until it could no longer support, the structure of the bridge could no longer support that that high amplitude of the wave. This is also, I think I gave an example with earthquakes, why sometimes buildings can come down when even a small earthquake occurs, because maybe not so much anymore, but it's possible if the frequency or the outside force of the earthquake consistently or persisted and ended up matching the natural frequency of a building, then it could increase the amplitude of the building, and maybe it would not be able to withstand that increase in amplitude. So resonance, outside force matches the natural frequency of an object. The next two have to deal with interference. We know that it is not very common for only one wave to be in a certain medium at a time. So if there are two waves that are in phase with each other, then they will constructively interfere with each other. When two waves constructively interfere, they keep the same frequency and wavelength, but the amplitude increases. So physically what this means, if you have two waves that constructively interfere with each other, they'll sound the same, the pitch won't change, but the amplitude or the volume will increase. So it'll just make a louder sound. And in phase with each other means that the waves are completely matched up in space with each other, meaning that the crests or the high points of that wave with sound, that's going to be the points of high pressure, and the low points of the wave, which are the troughs, or the points of low pressure and sound waves, completely match up with each other, are in phase, and that results in an increase in the volume or the amplitude. Destructive interference is kind of exactly like it sounds. It's going to be the opposite of constructive interference, and this is going to destroy parts of the sound, which is the process that is done for noise cancellation. So when two waves are out of phase with each other, then the amplitude will decrease, resulting in a decrease in volume or total noise cancellation if you have perfect out of phase waves in the same medium. So out of phase will be when the crest of the wave matches the trough of another wave, and vice versa. As they travel through space, their crests and their troughs match up with each other, resulting in noise cancellation, which just means that there's no decrease or increase in air pressure. There's no disturbance anymore. It's just homogeneous distribution of those air particles. All right, and then lastly, when does the Doppler effect occur? And that's going to be when either the source of the sound or the observer of the sound is in motion. So the important part here is that it's all about movement. If we know from examples in class and from the video projects and stuff that we saw yesterday, that the Doppler effect occurs when the source of the sound is moving. We saw cars, laying on their horn and driving by, and that produces a change in frequency to the observer that was standing off to the side of the road. But the Doppler effect will also occur if that car is sitting still, and maybe you're on a bike or you're running towards that car, and the observer of the sound, so the observer of the sound is now moving towards the source, you're also going to experience the Doppler effect. So if the source of the sound is moving or the observer of the sound is moving, and it can be either moving towards or away from that object. And the Doppler effect, remember that the Doppler effect deals with frequency, which means that it changes the pitch of the sound. And we know that as you get further and further away from a sound source, you're also going to notice a decrease in the volume or the amplitude of the sound, but that's not what the Doppler effect is talking about. That's what the inverse square law is talking about. So Doppler effect is frequency, and inverse square law is amplitude or intensity. All right, so it is important to be able to, excuse me, understand how to read the electromagnetic spectrum. This is, if you've looked at your equation sheet, this is exactly what will give you on the last page of your test, along with all the equations, obviously. So what you have here, the information that you have, is the order of the radiation, the types of radiation, and you also have this little visual here of how short or long the wavelength is. So remember, wavelength is measured the distance from any two successive same points on a wave. So if I was measuring the wavelength down here, I would measure from this crest to this next crest, and that would be the wavelength. So this tells you where the long wavelength is and then goes to shorter wavelength. What we don't tell you is that shorter wavelength corresponds with high frequency and also high energy. And conversely, long wavelength is associated with low frequency and low energy. So that's pretty much all you need to know. You don't have to memorize orders or anything like that. All you need to know is how energy and frequency are related to the wavelength, because we give you the wavelength here. So which type of electromagnetic wave has the longest wavelength? Again, you can tell that by the graphic. It's the longest distance between 2 points. And that will be at the very bottom of our graph here, which is our spectrum here, which is the radio waves. And then if we asked about highest frequency, we know, again, shortest wavelength is the highest frequency. The frequency is the number of cycles that pass by per second, and one full cycle is one wavelength. So if you have a really short wavelength, more cycles can pass by per second. So highest frequency is going to be gamma rays at the top of the graph, because that has the shortest wavelength. And then also, shortest wavelength means highest energy. And if you just think about the type of waves that we have here, remember, gamma rays come from the most energetic stuff in the universe, like supernova explosions. So it's going to, if you just think about the uses for these different types of radiation, it should make sense that gamma rays are going to be the highest energy, followed by X-rays. Radio waves are not too high energy. So gamma rays are going to be high energy. And then, of course, if you didn't have gamma rays as an option, you would select whichever one was closest to gamma rays for the highest energy. And then, so something like this, of the visible light part of the spectrum, so basically asking which color listed here, which one has the lowest frequency? And we know that the bottom is the low frequency end of the spectrum. So you're going to go to your list here and see which one is closest to the bottom of the spectrum, and your answer will be red light. So red light, of the visible light spectrum, red light will have the longest wavelength, the lowest frequency, and the lowest energy. And then, of course, at the other end, violet will have the opposite of that. And then lastly, at what speed does an X-ray travel in a vacuum? This is not a calculation, even though we're asking for speed. All light travels at the same speed in a vacuum, which is 300 million meters per second. everything on this list, even though we call light just what we can see, visible light, everything on here is light. So gamma rays, X-rays, microwaves, radio waves, ultraviolet, infrared, and visible light all travel at 300 million meters per second in a vacuum. Any questions? Yes, Sarah, go ahead.
Okay, just to confirm, so the ones that have the long wave, that would be the one that will have the low frequency and low energy, correct?
Long wavelength, low frequency, low energy. Yep.
Okay, and same thing with the colors of the spectrum.
Right. Yeah. So it's in order. So basically, if you think about anything on the bottom here, that's the longest wavelength, the lowest frequency, and the lowest energy. And then it goes in order. If you just move up the list here, move up the spectrum, it goes in order to the highest energy, the highest frequency, and the shortest wavelength.
Okay, perfect. Thank you.
Sure. Okay, one of the few calculations that we have for the wave part of our the wave section. Spring bobs up and down, completing 4 cycles in 2 seconds. If its wavelength is 2 meters, what is the speed of the wave? So if you go to your equation sheet and look for the wave speed equation, you should see that velocity is equal to frequency times wavelength. So here in this problem, we are given the wavelength is 2, and we want to know the speed of the wave or the velocity of the wave. Either way is fine. But we're missing the frequency. So the information that we are given is the number of cycles that it completes per second. And that just happens to be the equation for the way that we calculate frequency. The definition of frequency is how many cycles pass by a given point each second. So I go to my equation sheet and I see that frequency equals number of cycles per second. So I need to use that information to solve for the frequency before I can solve for the speed of the wave. So frequency equals 4 cycles per 2 seconds. 4 divided by 2 is just 2. And then we see that the frequency is 2 hertz. Now I can solve for the velocity or the speed of the wave, which is frequency times wavelength. This lambda symbol is our wavelength. And just plugging in our values, we end up with 2 times 2, and we end up with a velocity of 4 meters per second. So that is one way that we can solve. That is one equation that we can use to solve for wave speed. Frequency times wavelength is a specific equation for the speed of a wave, but it does not discount our previous velocity equation, which is distance divided by time. So keep in mind, depending on what you're given in the problem, if you're given distance and time as opposed to frequency and wavelength, you need to use a different equation to solve for the speed of a wave. There are 2 different ways to solve for the velocity. All right, and then I think lastly, what are the complementary colors? Again, this is the way that I remember it. I always write out RGB CMY, and what complementary colors are the colors that are added to the primary colors in order to create white light. So our 3 primary colors in physics are red, green, and blue, and they are our primary colors because adding together red, green, and blue light will give us white light. So these colors right here are basically, sometimes they're called the subtractive primary colors, because this is what happens, this is what you get if you remove any of the primary colors from white light. So white minus red will give you cyan. So basically it's just a subtraction of the other colors. So if you add that back in, if you add cyan back in, then you can get red light again. Oh, sorry, I didn't say that correctly. basically what you need to remember is that these two colors will equal white light. So blue and yellow, when you add blue and yellow light together, you end up with white light. Green and magenta together will give you white light, and red and cyan. So whatever is underneath the primary color, when you write it out like this, that is the complementary color. Oh, not lastly. All right, what type of field or fields does a charged particle at rest possess? So charged particle, either positive or negative, is going to be surrounded by only an electric field. Anytime you have a charged particle, it's going to be surrounded by electric field, meaning that that space around the charge is altered so that if another charged particle enters into that area, into that electric field, there's going to be a force that results in the change in motion of that particle. So if we have a positively charged particle, it's going to have a electric field surrounding it, and if a negative charge enters into that field, it will be attracted to that charged particle. If another positive charge enters into that field, then it will be repelled. So electric field alters the space around any charged particle. And then if we ask you what type of fields does a charged particle in motion possess, then that's going to be both an electric field and a magnetic field. When a charged particle starts moving, it does not lose its electric field. Sorry, my dogs are always fun during go-to sessions. Hold on a second. Okay, sorry. So a charged particle does not lose its electric field once it starts moving, but it does gain a magnetic field. So remember, the source of a magnetic field is a charged particle in motion. So if something's sitting still and then it starts moving, what it picks up at that point is a magnetic field. All right. Well, that is all I have. Do you guys have any other questions? Any other material that you wanted me to cover? Yes, Sarah, go ahead.
Yeah, I have some questions regarding the chapter 6 worksheet.
I'm sorry, what was that?
Yeah, I have some questions regarding the worksheet that we did for chapter 6.
Okay.
Okay, so it's going to be regarding the problem that we saw. They were saying a dolphin squeaks at a fish and its echo returns after 0.3 seconds. The sound wave travels at a velocity of 15-20 meters per second through water. How far is the fish from the dolphin? Now, when I use the velocity consistency over time, I got a different answer than the one that was there.
Yeah, so you're exactly correct. You're going to want to use the velocity equals distance over time equation, but what it gives you, did it give you the time or did it give you the distance?
I know it gave me like a different number than the answered.
What did the problem give you again?
Okay, so I did 1520 multiplied by 0.3, and that was 456.
Okay, so it gave you 0.3 for the time, right?
Yeah.
Okay, so where the discrepancy is that was the time, if you read the question, that was the time that it took for the dolphin to produce the sound and for that to travel out, hit something else, and then come back. So that time was actually double the distance from the dolphin to that object. Does that make sense?
Oh, okay, so then the answer would be if we divide that by 2.
Perfect, yeah.
It's 220. Okay, perfect.
Yeah, kind of tricky on that one because it's giving you the time that it took to reflect and go back, but the distance, the time that it took to just get to the object, which is what we need to know to solve for that distance, is half of the time that it took to reflect and come back. So it's kind of a tricky one.
Yeah. Okay, perfect. And then for number for number 17, that I was asking, what is the frequency of a wave that has a period of 0.5 seconds? Now for that one, we would use the frequency, which is equals to one over the time,
Hmm.
and then equals 2. Now my question is, would it be okay if we would have leave just like 1 over 0.5?
We don't really like to keep. It's not good math form to keep decimals in fractions, so it's better to reduce that and make that and make that 2.
Okay, so even if it gave us like decimals, or it's always better to just solve the fraction, correct?
Yeah, so if it gave you the period or the frequency was a whole number and it was like, say it was just 2 and you do 1 over 2, you can certainly leave that as 1 over 2. But if we give you the frequency or the period as 0.5, then you don't want to leave it as 1 over 0.5 because then you have a decimal inside of a fraction.
Okay. Okay, perfect. And then when it asks us what is the relationship between wave speed and frequency, and I know the answer was wave speed is directly proportional to frequency. That would be like we could obtain that answer by looking at the wavelength equation, correct? Or the wave speed equation.
Right, yeah, so that's right here. The velocity equals frequency times wavelength. So since the wavelength, the lambda symbol here, and velocity, they're both, we could put all these things over 1 because they're just by themselves. So they're both on top of a fraction on either side of the equal sign, meaning they're directly proportional.
Okay. All right, perfect. Yeah. And just to confirm, when you say that the constructive interference occurs, and it's when its two waves are in phase, when you say that they're in phase, is because they're overlapping?
Yes.
Okay.
Yep. If you put them on top of each other, if you drew that sine wave and you put them right on top of each other, it would look like the same one because they would look exactly the same. It would just look like
Oh,
one line.
okay, perfect. And then, and the last question regarding the generator, when we're reviewing right now, what does a generator do?
Hmm.
And it converts mechanical energy into electrical energy. When it talks about, I know you were explaining the mechanical energy would be because the generator was in motion, so that would be considered mechanical energy, correct?
Yeah, that would be the energy of motion or of moving parts. So if you think about the hand crank example that I was giving, you're taking your hand and you're physically moving part of that generator. So that motion is the mechanical energy.
Okay. Okay, perfect. Okay, that was my question. Thank you so much.
Oh, sure. Did anyone else have any other questions? All right. Well, that is all I have prepared. I will stick around. I'll be around for a little while longer. So if you guys think of anything, you can always sign out, log back in. And if not, then I will see you at the exam tomorrow. Thank you, guys.
Thank you. Have a good one.
You too.